Okay, let's get started. Can you all hear me clearly? All right, so what we're going to do is we're going to first go back to this linearized gravity approximation that we derived last time. So in the limit of a static source, okay, the static fluid stress energy tensor. So we're in the frame where the velocities are 0. So T mu nu just takes the form rho 0, 0, 0, 0, 0, 0, 0, 0. Okay, so this is the coordinate system in which there's a fluid which takes this form. That's our assumption. And in that coordinate system, we found the metric. Okay, and the metric works out to be this. Yeah. Oops. Okay. Yeah. So the metric works out to be of this form. ds square is -1 plus 2 phi over c square dt square 1 minus 2 phi over c square dx square plus dy square plus dz square. Okay. So I was not very careful with keeping track of the factors of c when deriving it, but you can always stick in the factors of C by dimensional analysis. So phi is the gravitational potential, which is gm by r. We know that if we multiply this by a mass, then it has dimensions of energy. Okay, so this has dimensions of energy. Energy by mass has dimensions of c square. Okay, so gm by r has dimensions of c square. So gm or phi divided by c square is dimensionless. Okay, that's why I stuck in the factor of c over here. Because this is added to a dimensionless quantity, I need to make it dimensionless. And the c square dt square, as usual, we can stick in the factor of c. Okay, so this is how you can always drop factors of c and always reintroduce them later when you actually have to plug in numbers or something. Okay. In fact, you can even do the same thing for g. Okay, you can drop g, set g equal to 1, and then stick it back in based on dimensional grounds wherever it needs to be. Okay, and that's conventionally what's done in lots of GR textbooks. Okay, I'll just keep the g explicit. Okay, so now the thing we have to do is we have to show. So we showed that this phi, okay, this phi satisfies Poisson's equation. So we show that this grad square phi is equal to 4 pi g n rho. So we showed it satisfies Poisson's equation, and this originally came from the fact that in the particular gauge we were working in, we had a wave equation that looked like this. Okay, and we just redefined gamma bar 0, 0. Sorry, not gamma bar, h bar 0, 0. Okay, we redefined h bar 0, 0 in terms of phi by scaling by a factor of -1/4. Now, of course, you could have always rescaled by something. The point is that once you've defined a phi this way, okay, you've got Newton's laws correct in the sense of the gravitational source term is correct. But what about particles moving in that gravitational field? Do they obey the right law? Okay, so that's the next thing that we're going to show. We're going to look at the motion of a test particle in the presence of this background metric. Okay, and we're going to see what that motion is, and we'll see that the motion of a test particle in this background metric will exactly give us, in this coordinate system, it will exactly give us Newton's laws, where mass times acceleration will be minus the grad phi, okay, where phi is the gravitational potential. Okay, so the geodesic equation is this. This is the general form in any coordinate system. Okay, and now what we're going to do is we'll also assume that the test particle is slowly moving. Okay, so the test particle also has a speed much less than the speed of light. So dx mu d tau for this particle is approximately 1, 0, 0, 0. Okay. However, from this equation, what we're trying to do is trying to find the rate of change of this. So the initial condition is it's small, but then we want to figure out what is the rate of change of that velocity. Okay, so we want to solve this equation. Okay, with the condition that dx mu d tau is approximately this. So this quantity can still be large. That's the acceleration. It's the rate of change of this quantity. Okay, so d square x mu d tau square. But here we can just plug in this 1, 0, 0, 0, 0. Okay, so when we do that, we just have minus gamma mu 0, 0. Okay, and then dx0 d tau, which is 1. Again, dx0 d tau, which is 1. So we're solving this equation. So we only need to work out this Christoffel symbol, gamma mu 0, 0. Okay, so gamma mu 0, 0 is half g mu sigma partial g 0 g sigma 0 plus partial 0 g 0 sigma minus partial sigma g 0, 0. Okay, and again, g, okay, is eta plus h. Okay, h is first order. So when we differentiate this, we will really just treat it as differential with respect to h. The second thing is we assume the sources were static, which means that h is only spatially dependent, doesn't have time dependence. So these two time derivatives disappear. You only have this term. Okay. And so sigma is only the spatial part. So even though sigma is summed over 0, 1, 2, 3, you only take the component where only the sum where the terms in the sum where sigma is 1, 2, 3. Okay, those contribute. So you get minus partial I. So the I is generally when you use I, you mean I runs over 1, 2, 3. And when you use a Greek letter like mu, you mean mu runs over 0, 1, 2, 3. Okay. So this partial I just is to remind us that this runs over 1, 2, 3. And I've only kept this term minus partial I h0, 0. And over here for capital G, since we're only evaluating the Christoffels to first order in H, okay, we can just take G to be the leading order metric, which is eta mu I, okay, eta upper mu I. And so now if I work out gamma I 0, 0, 0, okay, so these are the only ones which are going to be non-zero because eta mu I is non-zero only when mu and I are the same. Okay, so this is eta I minus partial I 1 plus 2 phi. Okay, and now what I get, sorry, this is h is just 1 plus 2 phi. Sorry, h is just 2 phi. Okay, h0, 0 is sorry, h0, 0 is minus 2 phi, is that right? What did we derive for h? Yeah, h0, 0 is minus 2 phi. Yeah, that's right. So h0, 0 is minus 2 phi. Okay, and we have a minus 2 phi here. Okay, and so now what this gives us is it gives us eta I is 1. Okay, minus partial I is, so this is, so now you have to be a little careful. The I index is not summed over here. Okay, this I index is, so basically, okay, so what I've done is I've really written this as gamma j00. This is eta ji minus partial I. Okay, and now when I sum this over over I, okay, what I'm going to get is a delta ji. Okay, so in the end, this will just be partial j phi. Okay, so this times this eta ji is delta ji. Delta ji times partial I is just partial j. And I'm not careful about upper or lower indices here because the spatial parts anyway stay the same with our metric convention. Okay, the spatial part partial j is the same as partial j. Okay, it doesn't really matter. Okay, this is with our metric convention, but you should be careful because partial 0 is not the same as partial 0, right? This is plus partial t. This is minus partial t. Okay, with our metric convention. Okay, so now we have partial j phi. So now what we can do is we can plug into this equation. So we have the components where mu is 0 and we have the components where mu is I. If we take the component where mu is 0, we get d square t d tau square is equal to 0. Okay, because we're now looking at gamma 0, 0, 0 and this is 0. Okay, by the fact that if I plug in mu here, eta 0 I will be 0. Okay, so for the t equation is very simple. It tells us d square t by d tau square is 0, which means t is some constant times tau plus beta. Okay, now this constant beta is just an offset. That's where I can choose to start the origin of my time. Okay, the scaling by alpha is just an amount with a constant amount by which I say, okay, instead of measuring proper time in units of 1 second, I'll measure it in units of some constant times 1 second. Okay, so I'll measure it in minutes, let's say. Okay, so this is kind of trivial. Okay, you're really measuring the proper time of a particle. Okay, so we can choose to set t is equal to tau. Okay, by choice of these constants. Now, the other equation gives us the other components of this equation where mu is equal to I. They give us d square xi d tau square is equal to minus gamma I 0, 0. Okay, and gamma I 0, 0 or gamma j 0, 0 we worked out as partial j phi. So we get a minus partial I phi. Okay, so now what this is it's really just the equation. These are the components of a vector equation. The vector equation is d square x bar dt square is equal to minus grad phi. Okay, if I multiply both sides by the mass, I get exactly Newton's law. Okay, mass times acceleration is minus the force. Okay, where the force of gravity, this is the force of gravity, where the force of gravity is minus m grav phi. Okay, where phi is the gravitational potential. Okay, so this is rather amazing, right? I mean, we recovered Newton's second law in the presence of a gravitational potential in the weak field approximation. The additional assumptions we made, besides the fact that the field is weak, that is phi over c square is much less than 1, the other assumptions that we made is both the sources and the test particles are moving with speeds much less than the speed of light. Okay, under these assumptions, we recover exactly Newton's laws. Okay, both for how the sources produce gravitational fields, which was this equation. Okay, and also for the action of these gravitational fields on test particles. Okay, they give you exactly Newton's laws. Okay, now that's rather interesting, right? It tells you that something is right with GR. Okay, but here's an interesting point, viewpoint in GR. Okay, see, the viewpoint in GR is that a particle in free fall in a gravitational field is following a geodesic. Okay, which means that this particle that we wrote down, this test particle, is the way we had thought of it. Okay, in general relativity, the viewpoint is that this particle is not experiencing any forces. It's an inertial object. Okay, it's under free fall in a gravitational field is really just inertial motion. Okay, this is not the point of view that we had taken in Newtonian mechanics. Okay, in Newtonian mechanics, the viewpoint in Newtonian mechanics is the particle is a particle in free fall in a gravitational field is not following a straight line. Okay, rather the particle is following a curved path in a background space-time. Okay, so by a curved path, I mean it's not the path that it would normally follow in the absence. This is the path that it would normally follow. Okay, in the absence of a gravitational field, and this is what we thought of as a straight line. Okay, but now what we're saying is no, it's really this equation that is describing a straight line, the straightest possible line, but that straightest possible line is in a curved space-time. Okay, how do we visualize the curvature of the space-time? As I told you, it's very hard to visualize the curvature because we're now in 3+1 dimensions, as opposed to 2 dimensions where it's easier to visualize curvature because there's just a single quantity that describes curvature, and you can think of the curvature as due to the embedding in 3 dimensions. 4-dimensional curvature is much harder to visualize because you need to talk about it in terms of the Riemann tensor, okay, which has 20 independent components in 4 dimensions. Okay, so we recovered Newton's second law in the presence of the gravitational field. Okay, and okay, so instead of so the point of view that we're taking now is radically different. Okay, so even though the equations look the same, okay, in this weak field limit, really our interpretation is what has changed. Okay, and that is really the big picture. Okay, that the particles are just following a straight line in curved space-time. That's the viewpoint in general relativity. The viewpoint that we were taking before was that the particles are not following a straight line because this is what we thought a straight line should be. Okay, it should be just something like x is equal to vt plus constant. Okay, we thought this is the rule that they should follow. So really, the observers who claim that the metric is eta, okay, and not eta plus h mu nu, those observers are actually the accelerating observers. They are non-inertial observers. Okay, it's really the observers who are seeing eta, the coordinate system in which you get this full metric. Okay, that system of coordinates. Okay, that is and if you are freely falling in this system, okay, where you see this metric, then you are what are called inertial observers. Okay, any questions at this point? Okay, so now what we're going to do is, it's one thing to get Newton's laws, okay, but obviously general relativity is much more rich, okay, than just getting Newton's laws. Okay, yes, you do get Newton's laws in some approximation, but now we can actually see that the linearized gravity theory, okay, not even the full theory of general relativity, just this linearized approximation to general relativity, actually gives us some really remarkable predictions. Okay, So I've listed some of those predictions here, and we'll try to talk about them. Okay, so today we'll cover these three, which is gravitational time dilation, gravitational redshift, and gravitational lensing. Okay, we'll talk about these three. Maybe next time we'll talk about gravimetric and gravomagnetic fields and gravitational waves. Okay, so for today we're only going to talk about these three. So let me start with the first one, which is gravitational time dilation. Okay, so what we're going to see is really new effects beyond just what you would expect from Newtonian gravity. Okay, and these are really just going to be predictions of this linearized general relativity. So the metric in a weak gravitational field we've already written down. Okay, it's just this metric. Now let's consider the potential due to, let's say, of the form minus gm by r. Okay, this is, let's say, due to either a point charge or a spherical mass distribution. We're assuming we're far enough away from this distribution, okay, which is true for any object like the sun. Even if you're at the surface of the sun or the earth at the surface of the earth, right, the gravitational field is weak. Okay, so so we've seen that it's a good approximation to use, okay, this weak gravity approximation, okay, near the surface of the earth. So we'll assume this kind of potential. Okay, so now let's assume this is the mass. Okay, you can either think of it as an extended mass or a point mass, doesn't really matter. We're far enough away that it doesn't really matter. Okay, and it has this potential, and you are, let's say, at this distance r1. Okay, now let's consider two different test objects which are held at different distances. Okay, they're held, which means they're not freely falling, they're held in place. One is at r1, one is at r2. Okay, and these objects, because they're held in place, okay, they are not following geodesics. Okay, they're following non-geodesic motion, but they will still follow a time-like curve. Okay, because if they don't follow time-like curves, that would violate causality. Okay, so they are non-inertial observers, but they're being acted on by this gravitational force of this mass m. Okay, so these are observers just being held at these 2 points. So you take something above the surface of the earth and hold it there, right? So if I pick this up and hold it at some height, that's the kind of object that I'm thinking about. This is a non-inertial object because only objects in free fall in general relativity are really inertial objects. Okay, that's the viewpoint that we take now. Okay, so in terms of our manifold, okay, if you want to think about it in terms of the manifold, the picture is that one object is at t1 r2, one object is at t1 r1. Let's say at the initial time, one is at r1, one is at r2. This object follows a trajectory which keeps it at r2. It's always at the same r2 coordinate, but only its t coordinate is changing. So its t1 goes from t1 to t2. And the second object, which is at t1 r1, moves along some curve, okay, where only the t coordinate is changing, and now it becomes t2 r1. Okay, so now what we want to do is okay, so the arc length along these curves is something all observers agree on. Okay, that is this arc length and this arc length. Okay, so sorry, I should really call this t1 prime and t2 prime. Okay, this is some initial time coordinate for this observer, this is some final time coordinate for this observer, this is some initial time coordinate for this observer, and this is some final time coordinate for this observer. Okay, so the arc length along these curves is something that all observers agree on, which is coordinate independent. Okay, so this arc length, even though it's not a geodesic, it's an arc length. Okay, and that arc length is something that all observers can agree on. That arc length is coordinate system independent. Okay, similarly for this curve, the arc length is coordinate system independent. Now, what is an arc length? The arc length is, okay, or the absolute value of the arc length, since this is a time-like trajectory, the arc length, okay, is going to be something like this. Okay, it's going to be square root of minus g mu nu dx mu dx nu. Okay, why the minus sign? Because time-like trajectories have negative inner product of dx mu dx nu. So I take it with a minus sign. Okay, and now this ds, this is minus ds square. Is this? Okay, and sorry, ds square is this. Okay, and this quantity is negative, so I take a minus sign and I take the square root of this. Okay, that's how I define the arc length. So this arc length ds, okay, is going to be, now since I'm not changing my my xi coordinate, I'm only changing my t coordinate. Okay, so my arc length is going to be, and so I have to integrate this. My arc length is going to be square root of minus g00 dx0 dx0. Okay, and dx0 is just dt. Okay, so I pull out the dt, and minus g00 from this metric is just 1 plus 25. Okay, minus of minus 1 plus 25, so it's 1 plus 25. So it's 1 plus 25, sorry, it's 1 plus 25 raised to half, okay, because I took the square root over here. Okay, so it's 1 plus 25 raised to half times dt. So now basically if I have an observer, okay, and for this observer t2 minus t1 is some delta t, okay, then the arc length along this curve is square root of 1 plus 2 phi, because phi is not a function of time, I can pull it outside the integral. Okay, 1 plus 2 phi raised to half times delta t. Okay, that's the arc length. All observers will agree that this arc length has a meaning. It's a coordinate independent meaning. Okay. Now the question is, what meaning do we assign to this arc length? Okay, what is the meaning associated with this arc length? So in the midsem, you've seen that in Minkowski space, if you take a time-like curve, okay, so you take some time-like curve, okay, it doesn't actually have to be a geodesic, and I calculate, okay, what is the proper time along this curve. Okay, so the proper time is the integral of d tau, which is integral of square root dt square minus dx square. Okay, this gives the proper time experienced by a particle. Okay, so square root of dt square minus dx square, if I integrate along a trajectory, this is in the case where g mu nu is eta mu nu. Okay, then I would get exactly the proper time, the time experienced by that particle. Okay, in a clock moving with that particle would experience this amount of time. Now in general relativity, okay, in general relativity, if you take any time-like path, we just generalize this idea. Okay, this arc length basically has the interpretation of being proper time. Okay, this arc length is, in general, the metric is not eta alpha beta, eta mu nu. Okay, but now this arc length has the interpretation of still being the proper time. Okay, so it gives the proper time experienced by a particle. All right. So for our two different observers now. So if you take this observer 1 and observer 2. Okay. If you take observer 1 and observer 2, the time elapsed, okay, delta tau 1 for observer 1 and the time elapsed for observer 2 will be different because they see different metrics. Okay. The first observer sees 1 plus 2 phi, but at their location, which is at R1 raised to half times delta t. Okay. The second observer sees 1 plus 2 phi R2 raised to half times delta t. Okay, where delta t is the amount of t coordinate that has changed. Okay, the change in the t coordinates. Yeah. Sorry, can you be real loud? Sorry, I really can't hear you. You can pull on your mask and just ask a question. Yeah, okay, so that's a good point. Okay, so delta t could also be different. Okay, this delta t could be a delta t prime in general. Okay. Now, what is the interpretation of this delta t? Okay, so if we are at r, which is very, very large, okay, so r tending to infinity, then delta tau 1 is the same as delta t. Okay, so if r is very, very large, you are very far from the gravitational potential. Okay, if you're very far from the gravitational potential, then an observer who is measuring a time delta t is really measuring proper time for themselves. Okay, so some observer who's sitting very far away, okay, and is measuring a delta t in this coordinate system is really measuring their own proper time. That's the time that they would see on their own clock. So an observer very far from this gravitational potential, so this is a mass, and this is x, you're somewhere very far. If you measure a coordinate time delta t that has elapsed, you're just measuring proper time. Okay, so that's really the rate that you'd measure on a clock, which is with you. Okay. However, if you have these two observers who are at some R1 and R2, which are not very far, okay, from this mass, then they will experience a delta tau 1 and a delta tau 2, which have elapsed. Okay, and let's assume that the same time delta t has elapsed for an observer who is very far away. Okay, but for these two observers, the time that would have elapsed is 1 plus 2 phi r1 to the half times delta t and 1 plus 2 phi r2 to the half times delta t. Okay. So, so time passes at a different rate for observers who experience different gravitational potentials. Okay, so if I am sitting in a deeper gravitational potential, that is phi r1 is negative. Okay, remember phi r1 is negative. Okay, negative but small. We're not assuming it's a very large number. Okay, phi r1 is negative, right? Phi r1 is, let's say, minus gm by r1. Okay, so if you're sitting deep in the gravitational potential, that is r1 is small, r1 is not large, then this term, the magnitude of this term gets larger. Okay, and if the magnitude of this term gets larger, okay, you're subtracting off this term from this. Okay, and what that tells you is this quantity is less than 1, and it's getting even smaller than 1 the deeper I fall into the gravitational potential. Okay, so the closer I get to the surface of the Earth, the closer I get to the sun, okay, the more delta tau 1 will become smaller than delta t. Okay, which means that clocks near the surface of the Earth, which are deep in the gravitational potential of the Earth, compared to a clock which is far away in space, okay, the clock near the surface of the Earth is going to experience less time passing. Okay, the clock near the surface of the Earth is going to, in other words, experience time dilation. Okay, the clock on the surface of the Earth will be ticking slowly compared to a clock which is very far away from the surface of the Earth in deep space. Okay, so we see that time passes at a different rate for different gravitational potentials. Okay, delta tau is 1 minus 2 gm by r to the half times delta t. And as we've seen, as r goes to infinity, there's no effect. Okay, so deep space clocks, which are far away from everything, okay, those clocks really are running and experiencing proper time as the coordinate time. But clocks which are placed deep in the gravitational potential, they will appear to run slower than clocks higher in the gravitational potential. Of course, I have to bring the clocks together to compare the times, or I have to communicate, for example, what is the time that has elapsed on one clock versus another clock, right? But for the same amount of delta t that has elapsed, okay, and this delta t has a coordinate invariant meaning, okay, it's the time seen by an asymptotic observer. Okay, for the same delta t that has elapsed, two clocks placed in a gravitational field, okay, will experience different rates of ticking. So, in fact, you can do an experimental test of this in principle, which is you have one clock high up on a tower. So you just climb to the top floor of this building, okay, versus a clock on the ground floor of this building. And you measure the time that has elapsed, okay, on one clock versus the time that has elapsed on another clock. So you synchronize the clocks now, okay, and you take one clock up to the top of the building, okay. And then after some time, you bring it back down and you compare the time that has elapsed on these two clocks, okay. What you will see is that the clock at the bottom of the building, which is deeper in the gravitational potential, this clock will have run more slowly. So this clock, let's say 15 minutes have ticked, this clock only 5 minutes would have ticked. Okay. Of course, you would have to build an extremely tall tower for this to happen. This is an extremely weak effect. Okay. So more realistically, let's try to estimate what kind of numbers you would get. Okay. How much would the extra time dilation be? Okay. So delta tau is 1 minus 2 gm over c square r to the half times delta t. Okay, and this 2 gm over c square, I told you we can define a quantity called the Schwarzschild radius, okay, which is 2 gm over c square. And for something with the mass of the Earth, that radius is about 8.9 millimeters. I said 3 millimeters last time, okay. The mass of the Earth is a little bit larger, so it's actually 8.9 millimeters, about 9 millimeters. Okay, so now, if you're at any distance, which is, so if you're, let's say the surface of the Earth, you're at a distance r, which is something like 6,400 kilometers. It's much, much larger than rs. Okay, so this rs is just some constant. Okay, so you're experiencing weak gravity, as we all appreciated already. Okay, so in that approximation, I can expand this factor, okay, using the binomial expansion. So this is approximately 1 minus half rs by r times delta t. Okay. I've just kept the leading order piece in rs by r. Of course, there are corrections of order rs by r square and so on. Okay, this is a further approximation to linearized gravity. Okay, just be careful about this. Okay, there's a further approximation that I'm making now. Okay, to this linearized gravity approximation, and now we are considering two clocks. Okay, so one on the so now let's take a more extreme example. So one clock is on the surface of the Earth. It's at 6,400 kilometers. Okay, another clock is a satellite. Okay, so typically, let's say this is the height of GPS satellites, okay, which are global positioning satellites, which are used to measure the positions of, let's say, cars, or even if you have a phone, if your phone tracks your location, okay, that's done by GPS. Okay, so now imagine that this GPS satellite is sitting at a height of 20,000 kilometers above the Earth. Okay, and the GPS satellite is very high. Okay, this is 6,400 kilometers. This is where we are. Okay, this is where us with our phones. The GPS satellite is here. Okay, and this height is an additional 20,000 kilometers. Okay, and let's imagine that there's a clock on board this GPS satellite, and there's a clock on your smartphone. Okay, and we want to compare what is the difference in the rate of ticking of these two clocks. Okay, so delta tau 1, okay, which is, let's say, for you, okay, sitting here at R1 versus at R2, okay, where R2 is this total height now, okay, or this total distance from the center of the Earth. So the total distance from the center of the Earth, R2, is 26,600, 20,200 plus 6,400. Okay, so delta tau 1 by delta tau 2, if I use this approximation, okay, it's 1 minus half, 8.9 millimeters. So I have to convert 6,400 kilometers into millimeters. So it's 1 kilometer is a million millimeters. Okay, so 8 to 10 to the 6. And the clock ticking on the GPS, okay, experiences this time dilation. Okay, both of these are sometimes some delta t. Okay, and that delta t is common, so that cancels out. So what I get when I multiply these out is delta tau 2, okay, is equal to, this is the time that has elapsed on the GPS versus the time that has elapsed on your clock. Okay, you would find, okay, because of course you can see that this is a very small number. Okay, I can make a further approximation. Again, this is a binomial expansion, so I can bring this to the numerator. It's like 1 minus x to the minus 1 and 1 minus x1 to the minus, 1 minus x1 over 1 minus x2 to the minus 1, which I roughly write as 1 minus x1 plus x2. Okay, that's by a binomial expansion of the denominator. To be more precise, let me just show you that intermediate step. I write it as 1 minus x1 times 1 plus x2. Okay, this is the binomial approximation to 1 minus x2. It's the denominator I've written as 1 minus x2 inverse, and this 1 minus x2 inverse is approximately 1 plus x2. Okay, so really I can write it as 1 minus x1 plus x2, which is what I've done here. Okay, this is 1 minus x1, and the second term is plus x2. Okay, times some number which is very small. This is 10 to the 6 times 10 to the 3. Okay, so I've basically pulled out a 10 to the minus 9. So you can see that this is going to be a very tiny number. Okay, you can check the number later. Okay, it turns out to be 1 plus 0.53 into 10 to the minus 10 delta tau 1. Okay, so what does this mean? Okay, what this means is, let's suppose delta tau 1 has ticked 1 second. Okay, so your clock on the Earth has ticked 1 second. Okay, the clock on the GPS has also approximately ticked 1 second. Okay, except it's actually gained a little bit extra time compared to your clock. Okay, it has gained an extra amount of 0.5 into 10 to the minus 10 seconds compared to the ground clock. Okay, so after 1 second has elapsed on your clock, approximately 1 second has elapsed on the GPS clock, plus this extra part, which is so tiny, 0.53 into 10 to the minus 10, you might think it wouldn't matter at all. Okay, but over the course of a day, okay, it would actually lead up to 46 microseconds of additional time that has elapsed on the GPS clock. Okay, you might still think that this is a very tiny amount. Okay, but what I'll show you is for GPS timing applications, to really, what does GPS try to do? GPS tries to localize your position. Okay, to try to give you a very accurate position to, let's say, down to, let's say, within 10 meters or 15 meters, tries to place where you are, let's say, on the surface of the Earth. Okay, so let's try to understand how precise this GPS timing information need to be. Okay, so imagine that I have two satellites. Okay, and what you really have to do is imagine that there are two satellites. Okay, maybe I'll just draw this picture again just to make it clear what's going on. So I have two satellites. So one satellite here, one satellite here. Okay, so we are sitting over here. Okay, so what we do is our cell phone sends a ping, okay, which is picked up by the satellite. Okay, and the satellite measures, okay, by on the clock on the satellite. Okay, it measures. So this ping is sent at the same time to both these satellites. Okay, it's sent at the same time. Okay, there's a clock here, and you can simultaneously send pings to both these satellites. So you send a signal in both directions. And let's suppose this satellite is a distance r1 away. The satellite is a distance r2 away. Okay, now this satellite will try to measure, the time on the satellite, okay, or the time it takes for the signal to reach here. Okay, so it measures, let's say, the time between two different pings. Okay, so so let's say that this time, okay, is the time it takes between two different pings is, so let's say it acknowledges the signal, okay, by sending a signal back, and then you send another signal, okay, to the satellite. So roughly speaking, the time that this satellite measures is R1 by C. Okay, this is the time it takes for a signal to go across, maybe by multiplied by a factor of 2 or 3, doesn't matter. Okay, so this is the time it takes for a signal to reach this satellite, or the time that elapses on this satellite's clock. Okay, you want to measure this time that is elapsing on this satellite's clock. And similarly, you measure the time that elapses on this satellite's clock. Okay, R2 by C. Now, when you measure the time that has elapsed on one satellite, this is giving you a distance. Okay, so you measured this time. Okay, and this time, by multiplying it by C, I know the distance to you. Okay, from this satellite. And similarly, I know the distance to you from this satellite. Okay, but with this satellite alone, I can only localize you on a circle because I only know the distance to you. I don't know where you are. Okay, I only know the distance. Similarly, with this satellite, I can again localize you to a circle. Okay, but by the intersection of these two circles, I can figure out exactly where you are. Okay, I've only shown this in 2 dimensions. In 3 dimensions, you need 3 satellites to triangulate your position. Okay, but let's just work with this 2D example for now. Okay, so now what we want to know is what is the error, okay, that we will get on measuring our position. Okay, so if we, let's say, measure an error in time. Okay, so we have some error delta T1. Okay, this will lead to an error in delta R1. Okay, in our measurement of position, and that error in position localization will now be smeared. Okay, so your position will be smeared over this distance, which is now delta R1. Okay, and similarly, if you have a ping error, okay, delta T2 here, okay, you will measure an error in your position, okay, somewhere like this, okay, which will be delta R2. Okay, and so within these two circles, okay, you're still localized your position to within this error region. Okay, so now it's a smeared out region. So instead of a point, you have a smeared out region. That's the error with which you localized yourself. Okay, so now suppose we want to localize ourselves. Okay, so let's calculate what is given an error on the GPS timing measurement. Okay, an error on delta T1 and delta T2. What is the error that we make on localizing our position? Okay, on the Earth. So T1 minus T2 is just R1 by C minus R2 by C. Okay, and the error on T1 minus T2, okay, if you know this error formula, okay, which you've taken a data analysis course, is square root of delta R1 square plus delta R2 square, where I've assumed that these are statistically independent errors on R1 and R2. Okay, so your error would be delta R by C. Okay, so this is the measured error. This is the GPS timing error. Okay, and this is the error that I want in terms of how well I can localize your position. Okay, so if I want an error uncertainty of 15 meters, I want to be able to localize you to within 15 meters. C is 3 times 10 to the 8 meters per second. So 15 meters over 3 times 10 to the 8 meters per second is 50 nanoseconds. Okay, which means that I need to measure times, okay, or times on these GPS satellites, okay, which are accurate to within 50 nanoseconds. Okay, the timings on these satellites need to be accurate to within 50 nanoseconds. Okay, now the clocks on these GPS satellites were calibrated on the surface of the Earth. Okay, when you take them up high above the surface of the Earth, their clocks are now running faster. Okay, they're running faster than what they're running on the Earth. So what will happen very quickly is, instead of getting, so you might think that you have 50 nanosecond precision, okay, but now your clocks are going to lose time. Okay, sorry, they're going to gain time very fast. Okay, so in particular, we've seen that in 1 second, these clocks pick up about, once you take them high above the surface of the Earth, these clocks are picking about every 1 second, they're picking up about 0.5 into 10 to the minus 10 seconds. Okay, which means roughly over 100 seconds, they will have picked up, okay, they will have picked up, let's say 50, yeah, they will have picked up about 50 nanoseconds of delay. okay, which means that already your uncertainty is going to be of the order of 50 nanoseconds. Your error is going to be 50 nanoseconds. Then after another minute, it'll be another, after another 100 seconds, it'll be another 50 nanoseconds of errors. Okay, so you'll keep making this error. Okay, so within less than 2 minutes, your uncertainty in position will be much larger, okay, than 15 meters. It'll within 2 minutes it'll become 30 meters. Within another 2 minutes it'll become 60 meters, and so on. Okay, so if you don't take into account this gravitational time dilation, okay, the fact that clocks deeper in the potential well are running slower, clocks taken high above the ground are running faster relative to those clocks, okay, you will make errors. Okay, so in order for your GPS to work, in order to for Google to triangulate your position, you need to take into account this GR correction. Okay, that's rather cool, right? I mean that there's an effect that has to be measured. Now, this effect is really simple in the sense that it's a constant shift, okay, for satellites at a constant height. So you could always make that correction and say, I don't know what happened to my satellite, it just stopped working and it's losing time, but I know I just have to make this constant shift. But now you know why you have to make this constant shift. It's really due to physics, okay? It's not because of an error in manufacturing, okay? Now, a much stronger time dilation effect should occur near the surface of a compact object like a black hole. Okay, so GPS is, of course, you have precision, okay, in what you need, and therefore you cannot tolerate, okay, even a small deviation. But if you want to really see an exaggerated effect of time dilation, you would have to go near the surface of a black hole. That is something that we have not done yet, okay? But we've seen objects or radiation which comes out from near the surface of a black hole. If you've seen the movie Interstellar, right, where in the movie these astronauts drop down close to the surface of a black hole, and for them, they're on a planet which is close to the surface of a supermassive black hole. Okay, these supermassive black holes with masses of 10 to the 6 solar masses are expected to exist near, for example, the center of our galaxy. Okay, and the center of most galaxies are expected to host this kind of supermassive black hole. Now there's this in the movie. Okay, there's a planet which is close to the surface of this black hole, and then there's a spaceship which is sitting high above. Okay, and so these astronauts, they drop down, okay, to the surface of this planet, and for them they only spend a few hours on the planet. Only a few hours elapse for them, so they only age a few hours. But when they come back here, the crew has aged many years. Okay, the crew has aged like 30 or 40 years. Okay, because time is elapsing faster. Okay, for the spaceship, which is not so deep in the gravitational potential, but the planet is deep in the gravitational potential. Okay, this kind of strong gravitational effect would only be important in near the surface of a black hole, as we've already discussed, near some very compact object. Okay, any questions here? Yeah.
So, I mean, sort of in the reverse side of here, but essentially to compare two clocks, you either have to basically bring them together or send light signals.
Yes.
If you're comparing two clocks together and then you're carrying one to the other place, then you could argue that, I mean, it's obviously an accelerated motion, so you could argue that it's the same thing that's happening like the twins power, and so it's not really a gravitational effect. So,
yeah, that's a good question. How do you argue that this is not due to um, that this is not due to accelerating them, right?
You just spend more time and more. If you leave them up for, example, 5 days and there's more of a difference than when you leave them up for 2 days, you actually the gravitational effect because the acceleration was same.
No, I think the point is that when you bring them together, in the process of bringing them together, maybe you are affecting the time on one. How do you know you're not? That's not what you're doing.
But you, if for example, you leave them apart for 100 days, you bring them together with the same acceleration.
Uh-huh.
And then you leave them apart for 1 day and bring them with the same acceleration. How can you say that, oh, even with the same acceleration, it's 100 times more?
Yeah, I think that's, well, that's sort of a proof that like it would have to be very contrived for this to be true. Doesn't rule out the possibility that acceleration did this, right? Yeah, so okay. So let's put it the other way. Time dilation by itself in a gravitational field may not be proof of general relativity, right? But it's a prediction of general relativity. Yeah. Other questions? Well, so what I claimed is that time showing that there is time dilation is a prediction of general relativity, but measuring time dilation is not necessarily a proof of general relativity as a whole. Right? So if you test the prediction and it agrees, it's an agreement with general relativity. So at least general relativity is not ruled out by this observation. Right? But let's say Newtonian, you have to have some other explanation for why the clock time dilated. Right? Yeah. The delta t is the same.
How exactly do we know that because it's far away, how is it the same delta t length from when we compared them first and we compared them the second? But then the same delta t is inverse.
Yeah, because one has the time elapsed are very distant observer who is basically observed. So it's not dependent on this observer.
But if there is specific proper time zones are different.
I mean, essentially it was something like this, right? You have a clock and you have a clock which is in beat. Then you solve out, you see a value delta t1 elastic on your clock and delta t is elastic on that clock.
No, but when you're comparing delta t, you're comparing these two together. So how do you know the difference?
Well, you can imagine comparing it with the faraway clock, right?
That is eliminating one.
Sorry?
You're eliminating that step.
We're eliminating that step, but in principle, we're assuming that that is happening, right? So I mean, you're comparing with the asymptotic clock, which is there's a clock here, right, which is really measuring delta t as the proper time. Yeah. Okay. Now let's go to the second prediction. Okay, which is gravitational redshift. Okay. So there are a couple of ways to derive this phenomenon of gravitational redshift. I'm just going to follow the approach of using time dilation, okay, to show that there's gravitational redshift. So here's the idea. Okay, you have a photon, okay, which I've denoted as gamma over here, in a gravitational potential. So this is at r1, and this is some other distance r2. Now let's assume that when the photon is emitted, it has a frequency nu1. Okay, and so let's say the time period between two peaks, okay, or if I think of it as pulses, the time period between, or let's say something like this, the time period between two peaks, okay, is t1, which is 1 by nu1. Okay, this is the time as measured on a clock which is over here. Okay, so t1 is 1 by nu1 is the time period between pulses at emission, right? And now if I have, and now this photon travels and is reaching over here. And we're assuming that this time period is very small compared to the time it takes to get from here to here. Okay. And we measure the time period between pulses at detection. Okay. And that time period, T2, okay, we'll assume that in general the frequency we detect is different. Nu is equal to nu2. Okay. So the time T2 that we measure between two peaks, okay, of this wave hitting, okay, are is T2 is 1 by nu2. This is the time period between the pulses at detection. Okay. Now, what we know from gravitational time dilation, okay, that the pulses that we send, okay, which are spaced t1 apart, okay, so the time it takes to travel is the same for both pulses. Okay, both pulses will take the same amount of time to travel because let's say the distance between these 2 points is not changing as a function of time. Okay, the metric is not time dependent. So the time it takes for these pulses to reach, okay, that time is the same, okay, for let's say the first pulse and the second pulse. Okay. Yeah, so the picture is in time, Okay, according to this person's clock, pulse 1 is sent at time t is equal to 0. The second pulse is sent at time t1. Okay, this pulse takes some time to reach here. Okay, and then this person starts their clock and says that that is time t is equal to 0. The second pulse takes exactly the same amount of time to reach here, and then this person says that a time t2 has elapsed on their clock. Okay, but because of gravitational time dilation, these times t1 and t2 are not going to be the same. Okay, so t2 will be equal to t2 by t1 will be equal to 1 minus gm over r2 raised to half times divided by 1 minus gm over r1 raised to half. Okay, so what that means now is that frequency 1 by frequency 2 will be equal to this factor, or wavelength 2 by wavelength 1 will be this factor, will be the same factor. Sorry. Okay, so now let's take the limit that R2 is much greater than R1. Okay, so if R2 is greater than R1, R2 is let's say deep space, R1 is deep in the potential. Okay, and this factor is smaller than 1. This factor is closer to 1. Okay, and so lambda 2 by lambda 1 is greater than 1, or lambda 2 is greater than lambda 1. Okay, so that means that photons which are climbing out of the potential well, lambda 1 is a photon which was emitted deep in the potential well, but when it reaches an observer who is outside the potential well, okay, or somewhere far above in the potential well, their potential, the wavelength of the photon gets redshifted. Okay, the wavelength becomes longer. So this experiment, there was an experiment done to test this in the 1960s, okay, called the Pound-Rebka experiment. And it verified this effect to within 10%. Okay, within the uncertainties, the actual effect was measured to within a 10% error. Okay, by sending gamma rays from the top of a tower to the bottom of a tower. Okay, and measuring the change in frequency of these gamma rays, or the change in energy of these gamma rays. And more recently, in the early 2000s, this was tested by gravity probe A, and it was tested to a precision of 1 part in 10 to the 4, which means if you predict a shift in wavelength, okay, by wavelength, which is some quantity, let's call that alpha, then you're measuring alpha to within 10 to the minus 4. Okay, that's the precision to which this effect has been tested. Okay. This effect is really similar to what you had worked out in tutorial 1, okay, for Rindler observers. So if you have Rindler observers in Minkowski spacetime, Rindler observers are accelerating observers. Okay, so one of the parts towards the end of the problem was, imagine you have an inertial observer who's falling beyond the Rindler horizon and sends a light signal. Okay, they send a light signal to the Rindler observer, which catches them at some later time. Okay, then what you calculated was that the Rindler observer sees a redshifted wavelength. Okay, they see a redshifted wavelength. Now this was really, we interpreted as, okay, the Rindler observers are accelerating, so they're seeing a redshifted wavelength. But really remember, Rindler observers are accelerating observers, but these accelerating observers, okay, by the equivalence principle, these observers are like static observers who are seeing a uniform gravitational field. Okay, they're observers who are being held above the surface of the Earth rather than falling towards the surface of the Earth. They're not in free fall, so they're really like the accelerating observers. So these accelerating observers, when they're sent a signal from the surface of the Earth by a free falling observer, they will see that signal as redshift. Okay. Okay, so this effect is called gravitational redshift. Okay, and this has been seen many times. Okay, in light signals which are coming out of deep potential wells. Okay, in fact you can use this to detect. Okay, so there's this radiation which comes from the Big Bang called the cosmic microwave background. Okay, and basically in regions where there was a lot of matter or a deep potential well, the light coming from that region, okay, is gravitationally redshifted. And regions which are underdense, okay, which have low densities, the light from there is relatively blue shifted. Okay. Okay. Yeah, and finally, let me come to the last thing that I'll discuss today. This is a third effect that you can see in the linear approximation. Okay, this linear approximation. So we've already encountered two new effects that, even though general relativity in the linear approximation predicts Newtonian gravity, it also predicts these other things. Okay, so it's not just that you're reproducing Newtonian gravity, you're really making new testable predictions. Okay. So one of these predictions is called gravitational lensing. Now here I'm not going to derive exactly all the equations of gravitational lensing. For details of the derivation, you can see this section in Sean Carroll's book. Okay, I'm just going to tell you the key steps and present the final formula. So the idea is that in general relativity, you postulate this, okay, that light follows null geodesics. Okay, in the absence of any interaction of the light, it's not getting absorbed or emitted. It's just following a null geodesic. And so what you want to do is you want to solve this geodesic equation, okay, but you want to solve it with the constraint that the tangent vectors, okay, are null vectors. That is, gxx is 0. Okay, in components you write it out like this. Okay, that is, the tangent vectors are always null. They have 0 norm. So one thing to note is that unlike what we did for time-like observers, okay, which is massive particles, we argued that lambda is, if lambda is an affine parameter, then lambda can be written as a tau plus b, where tau is the proper time experienced by a massive observer, okay, which is following a time-like trajectory. But for a null trajectory, okay, proper time is 0. Okay, no proper time elapses, but you can still define an affine parameter. It's just that this relationship, lambda is a tau times b, that is not a valid relationship for null geodesics. Lambda is still an affine parameter, though. Okay. So in particular, given one affine parameter, you can get another affine parameter by this, but lambda just does not have the interpretation of being proper time, okay, for light. Now, how do we see this? So let's go back to the familiar example of Minkowski spacetime. So if g mu nu is eta mu nu, then this gives us the equation. So the first equation just gives us d square x mu d lambda square is 0. The second equation, okay, for null geodesics just gives us, if I ignore the d lambda, okay, it just gives me g mu nu dx nu is 0, which is dx 0 square minus dx bar square is 0. Okay, so in other words, it's telling me that if I solve this equation, this will still give me a linear equation. Remember, x is equal to a times lambda plus b, t is some a prime lambda plus b. Okay, or it'll just tell you that t is linearly related to x. Okay, but it won't tell you that that speed is less than the speed of light, greater than the speed of light, or equal to the speed of light. That's why you need this additional condition. Okay, for time-like geodesics, we saw that v has to be less than c. For null geodesics, v is equal to c, and you just by this condition, and you just get x is equal to ct. Okay. Okay, so now let us consider the metric. So now, instead of just considering the metric eta mu nu, okay, let's consider a more general metric, the metric that we've derived in the linearized approximation. And let's work out what the null geodesics are. Okay, that is, what are the trajectories that light follows in a gravitational field, in a weak gravitational field. So we're taking the metric to be eta mu nu plus h mu nu. Okay, where h mu nu is minus 2 phi, minus 2 phi, minus 2 phi, minus 2 phi on the diagonal. Everywhere else it's 0. Okay, now since the metric is different, okay, you would expect that this would alter the trajectories of light rays. Okay, in other words, light will bend in a gravitational field. Even light gets deflected. Okay, because really this has nothing to do with the mass of the particle. Okay, the fact that it's following a geodesic is sufficient to ensure bending in your coordinate system, in the coordinate system t, x, y, z that we were using. So let's take our trajectory, okay, to be x mu of lambda, where lambda is some parameter that describes the trajectory. And again, since our gravitational potential is weak, okay, so phi is some, I'm not going to use lambda because I'm using lambda to denote the parameter of the trajectory, but let's say some epsilon, okay, phi is small, okay, phi is some epsilon keeps track of the fact that it's small. So our trajectory can be expanded order by order in epsilon. Okay, so our trajectory will be the trajectory that light follows in the absence of phi, plus some correction due to the presence of the gravitational potential. Okay, and this is a perturbation in the trajectory. Okay, so now what you can do is you can solve the geodesic equations. Okay, you can solve the geodesic equations for this perturbation in the trajectory. Okay, so instead of solving the so you take the geodesic equations, and we know our Christoffel symbols are first order. Okay, and now what we need to do is we need to solve for x mu now to first order. Okay, instead of solving to 0th order, we solve this for first order. Okay, so we can define a tangent vector dx mu d lambda, okay, again as dx0 d lambda plus dx1 d lambda, and this is k mu. Okay, this is, let's say, this is the sort of momentum or velocity of the light vector, and this is the deviation vector from straight line motion. Okay, so this gives us a deviation vector. So this is the tangent vector, and this tangent vector has the interpretation of velocity or momentum vector, and this is the deviation from of that velocity vector. Okay, as compared to from the straight line motion that you expect with a Minkowski metric. So what we need to do is now solve the geodesic equations at first order in the perturbations to find the new trajectory. Okay, so let me just describe pictorially what will happen when you solve the geodesic equations. Okay, and then we'll come to the math of it. Okay, so here's the idea. Okay, you have a distant star. Okay, so the star is over here, and you have us. This is us over here. This is a light ray that is traveling from the star towards us. Okay, and of course this is, I'm only showing this in space. I'm not showing this in time. Okay, this is only a picture in space, but of course at different instance of the time, the light beam is at different positions. Okay, now the tangent vector to this curve, the tangent vector in space time, okay, describes the four velocity or u mu, okay, or the four momentum rather, okay, p mu, okay, which in flat space time you would say something like e. If it's traveling along the x direction, it's just e 0, 0. This is what you would think naively is the tangent vector. This would be like dx0 d lambda. Okay, this would be like your tangent vector. Now, because of this perturbation, so now I introduce a mass. Okay, there's some mass in the middle, and this mass creates a gravitational field, and this light particle, as it's moving through this gravitational field, is now going to experience a deflection in its trajectory. Okay, so what is going to happen to this trajectory of light is that over time, the trajectory of this light will actually follow this path. Okay, at different instance of time, it will follow this kind of trajectory. So now when I see this light beam, instead of seeing it coming from this direction, I will now see the light beam as coming from this direction. Okay, so you at your location, you only perceive the light beam that hits you. Okay, the light that actually hits you. So you will see it as traveling in this direction. Okay, and so you will measure, if I extrapolate this backwards, okay, if I extrapolate this line backwards, I will see that light beam as coming from this direction. Okay, and so I will see the star as being at this position on the sky. So rather than being over there, I now see the star, or rather than being over there, I now see the star as being over there. Okay, at some different location in the sky. And that deflection angle here, okay, is measured, and it's denoted as alpha. Okay, and this is due to the gravitational potential generated by this deflection is purely caused due to the gravitational potential generated by this mass m that this light particle is passing through. Okay, now you have to solve those geodesic equations to first order to actually work out what is this deflection angle alpha. Okay, and you can show that the deflection angle alpha, okay, you can treat this as a vector. Okay, this deflection angle is a vector. So this is telling me that the vector is in this direction or in this direction, or in a perpendicular direction. So this vector, you can show it's written as 2 times the gradient of phi in the perpendicular direction. That is the gradient of phi in this direction. Okay, you would measure the gradient of phi in this direction times ds, where ds is the distance that the photon would have traveled, okay, along this direction. Okay, so I integrate this over the entire path, okay, and that gives me the total deflection angle. Okay, so what is happening is as the photon moves, at every instant of time, it picks up a little extra deflection, picks up a little deflection, picks up a little deflection, picks up a little deflection. And over the entire path, it picks up some very large deflection, okay, as it moves in this gravitational field. And if you solve the geodesic equation to first order, what you would find is that the total deflection angle is the integration of all these small deflections that it picks up, okay, which is 2 times this gradient of phi ds. Okay, I'm not deriving this. You can check out the derivation in section 7.3 of Sean Carroll's book. Okay, so S is this distance traversed, and this gradient of phi more generally is the gradient in the direction perpendicular to the momentum vector k, the direction of propagation of this light beam. So now what you can do is you can work it out again for the specific case of this gravitational potential minus gm by r. Okay, so if the particle is, or the light beam is over here at some r, okay, I'll denote its coordinate as, so this distance is b, okay, from the center of the mass, and I'll denote its coordinate of the light particle as x, okay, where x is equal to 0 is this point of closest approach, okay. So initially we'll assume it starts at x is minus infinity and it ends as x is plus infinity. So it starts very far from the gravitational potential on one side, ends very far from the gravitational potential on the other side. So at any point, okay, this distance r is the square root of x squared plus b squared, okay, where this particle is over here. Okay, r is the distance from the center of the gravitational potential. So I can write this r now as minus gm over square root of b squared plus x squared to the half. So the gradient of phi, okay, is now the derivative in, and I want the gradient in the perpendicular direction. That is, I want the gradient in the direction of b. Okay, so I want the gradient not in this direction, but I want the gradient in this direction, not in the radial direction, but in the perpendicular direction. So the gradient is partial b of this times b hat. Okay, and so if I work that out, I get gm over b squared plus x squared to the 3/2 times b, okay, times b hat. And if I plug this into that integral, okay, this gradient of phi, I'm integrating over ds, and ds is just x. Okay, x tells me how far along I moved along this path. Okay, so I'm integrating along x, where x goes from minus infinity to infinity. This b is a constant, so I pull it out. This is 2 gmb times dx over b squared plus x squared to the 3/2 b hat. Okay, or the magnitude of alpha is this integral, okay, and on dimensional grounds you can argue if I replace x by b sinh eta, it makes it easy to do this integral. But on dimensional grounds you can argue that if I make this kind of substitution, then I get a dimensionless integral, and from this integral I pull out dx gives me 1 factor of b, and this b squared plus x squared to the 3/2 gives me a factor of b cubed. So I get a 1 over b square, okay, which I pull out times a dimensionless integral. And the dimensionless integral turns out to be a factor of 2 when you work it out. Okay, so you get 4 gm over b times c square. That's the deflection angle. Okay, again, writing this in terms of the Schwarzschild radius, it's 2 rs over b. Okay, so let's look at this effect. Okay, so in 1919, okay, Arthur Eddington set out to measure this effect. So general relativity was proposed as a complete theory in 1915. Okay, 4 years later, in the peak of World War I, okay, Arthur Eddington took a trip to Africa to measure this effect. Okay, so I'll tell you why he had to go to Africa to measure this effect. Okay, so this is the sun. Okay, and this is the Earth. Okay, and the Earth goes around the sun. And now here is some distant star. Okay, and if you're over here, okay, if you're at this position, then it's nighttime on this side of the Earth. Okay, it's because this side of the Earth is away from the sun, and you can measure the position of the star, and you know where it is relative to other stars on the sky. Okay, so let's say it lies in some particular constellation. Okay, however, if you want to measure gravitational redshift, gravitational deflection of the light of this star, you have to be over here, and you have to measure the light from the star as it passes close to the sun. Okay, and you want to measure the effect as it passes close to the sun. But the problem with trying to do this measurement on when it's passing close to the sun is that you're looking at the star in daytime, okay? And you're looking at the star in daytime. So how do you look at the star? You can't see the star. So you have to wait for a solar eclipse where the moon is blocking out the sun. And when the moon blocks out the sun's light, you can see the star, okay? Ordinarily, if light traveled in a straight line, this light would be right behind the moon and therefore behind the sun, and you would not be able to see it, okay? If gravitational lensing exists, okay, and this light bends around the sun, then this light would get deflected and you would measure an apparent position of the star. This particular star would appear to be somewhere else in the sky, okay? So relative to the other stars, you would see that its position has shifted, okay? So to make this measurement, to see that the fact that the star has changed its position in the sky, you have to make this measurement during a solar eclipse, okay? So in 1919, there was a total solar eclipse in Africa. And so Arthur Eddington took a trip to Africa to measure, okay, the solar eclipse, this deflection of light, okay, and what he found was he found very good agreement with this deflection. So let's see how big an effect this deflection is, okay, how big an effect this is. So let's imagine that this light is passing right near the surface of the sun, okay. So it's just getting deflected around the sun. So basically the distance that this deflection, okay, is this deflection which we call B, is just the radius of the sun. That's what we're assuming, okay. So this effect is this angle is 2 times RS over R sun. Okay, the Schwarzschild radius of the sun is 6 kilometers. Okay, is 3 kilometers times 2 is 6 kilometers divided by 700,000 kilometers. So this number is about 10 to the minus 5 radians. Okay, which is 5 into 10 to the minus 4 degrees. Okay, it's a very tiny deflection that you're measuring on the sky. Here's a star that should have been just behind the sun, but now I see it 10 to the minus 4 degrees away from the sun. Okay, and so basically just outside the moon. Okay, so lensing is used was used to confirm this, and this was a spectacular confirmation of one of the predictions of general relativity. Okay, now the use of lensing has become much more ubiquitous. Okay, in physics. Okay, and we use this in astrophysics all the time. Okay, so lensing has been used to detect an invisible form of matter called dark matter. Dark matter has actually been seen in many other ways. It's believed to hold together galaxies. Galaxies don't have enough gravitational pull just to their visible stars to hold themselves together. If you look at a star, it's moving too fast. Okay, the gravitational tug is not enough to make it bend sufficiently to stay in orbit around the center of a galaxy. There must be some invisible form of matter holding such galaxies together. You can actually see such invisible matter through the gravitational lensing effects. Okay, gravitational lensing effects is an alternative way to see that such matter must be present. So, for example, if you look at galaxy clusters, okay, so these are so many spiral galaxies. Okay, these are believed to be surrounded by a halo of dark matter. So tons of invisible matter that you can't see, but you can see the starlight from these galaxies. So when you look at something like the Milky Way, you're only seeing the light of the galaxy, but there's a ton of mass, okay, which you can't really see, matter which is spread out. Okay, we don't know what this form of matter is. It's one of the big open questions in physics. What is dark matter? What is the fundamental particle that makes up dark matter? It's definitely nothing in the periodic table of elements, not made of protons, not made of electrons or anything like it. Okay, what it is still a mystery. Okay, but as far as the fact that it's a mass, what it means is it's going to have a gravitational effect, and you can detect it through its gravitational effect. That gravitational effect can cause bending of light. So if you look at objects called quasars, okay, these are very distant, very bright objects. Okay, you can see them to very far distances in the universe. Okay, and we can see many of them. Okay, so these distant quasars, they emit light, and this light gets bent, okay, in different directions as it passes through this matter field. And if this is us, we will see actually multiple images of this quasar, okay, due to the bending of light. So this is an image taken with the Hubble Space Telescope, okay, of this bending of light. Okay, so these circles over here are bending of light of a single quasar. It's a single quasar where you're seeing 4 multiply lensed images. Okay, and this shadow that you're seeing here, this blur, is a foreground galaxy. Okay, so there's a galaxy between you, or a cluster of galaxies between you and this background quasar. And what you're seeing, okay, are these multiple images of the quasar. Okay, and we've seen this in multiple systems. Okay, these are different galaxies, clusters of galaxies, in which the Hubble Space Telescope has seen these what are called strongly lensed quasars. Okay, if you're very closely lined up, that is, if the distant quasar is very well lined up with this galaxy, then you'll see this kind of strong lensing effect. Okay, if the background object is not very well lined up, then the effect of lensing is much weaker. Okay, because then the light is not passing so close, okay, to the gravitation, to the deep gravitational field. Okay, but you can still measure this effect, and it's called weak lensing in that case. Now, these multiply lensed quasar images actually turn out to be very useful for something else. Okay, so let me tell you about another effect of gravitational lensing, which again I'm not going to derive, but again from the geodesic equation, calculating the perturbation to the geodesic equation, you not only get a path difference in space, but you get a path difference in time for the light that travels from the source to us. That path difference causes a delay, okay, in the time or the clock that is moving with the light beam. So the light particle experiences an additional delay due to the gravitational potential, and that delay is -2 times just the integral of the total gravitational potential along the path the light has taken. Again, I'm not deriving this. Okay, you can see the proof in Sean Carroll's book. So in addition to this, there'll also be a geometric delay due to the fact that light coming from different paths is traveling different distances. That's a different effect. This effect is due to gravitational time dilation. Okay, due to gravitational time dilation, there's an additional delay. So the total delay will be the delay due to geometric effects due to the fact that the path it takes is longer, plus this additional time dilation effect, which is called Shapiro delay. Now, here's an amazing thing that you can do, okay, with this quasar image. Now, quasars are not very static objects. Okay, they're really believed to be massive black holes around which you have some kind of accretion disk. Okay, and as matter falls into this accretion disk, okay, it has experiences friction, and it basically emits radiation due to that friction, and this radiation is emitted in high energetic jets. Okay, so that's what you're seeing from this quasar. Now, as a blob of matter falls into the black hole, okay, the quasar basically erupts and it emits more radiation. So basically the radiation from this quasar increases rapidly in intensity. So this is called a flare. Okay, you see a flare from the quasar where it becomes much brighter. Now, if you have a lensed quasar like this, okay, what will happen is each of these lensing images will flare up. Okay, but each of these lensing images will have a different time delay. So each lens image will flare up at a different time. Okay, and so what you can do is you can measure these time delays between these different images flaring up, and the different time delays of the flaring up. Okay, in fact, these quasars were observed over 20 years, and this time delay between the flaring up is tens of years. Okay, like 5 to 10 years. So you have to wait that long. You see one image flare, 5 years later another image flares, 5 years later another image flares. Okay, so it's crazy that they had the patience to do this, right? But they took these measurements, and they found these time delays, and with these time delays you can in fact use this to do something wonderful. Okay, you can actually use this time delays to measure the distance to these faraway galaxy clusters. Okay, you can measure the distances pretty precisely to within few percent errors. Okay, with current data. And this turns out to be very useful if you measure the distance to distant galaxies. It turns out to be very useful for measuring the expansion rate of the universe. Okay, so in order to get this measurement of distance to these galaxies correct, you have to take into account this the Shapiro time delay and the geometric time delay, both. Okay, and finally, I'll just tell you, there's another way to think about this lensing effect. Okay, this lensing effect, we saw that we had this metric. Okay, -1 + 2 phi c square dt square plus 1 - 2 phi dx square. And for a null geodesic, we said ds square is 0. Okay, the proper time elapsed for a light particle is 0. So I can just equate this to 0, and that gives me the trajectory that a light particle moves on. Okay, So I equate this to 0, and so c square dt square is 1 minus 2 phi over 1 plus 2 phi dx square. Or in the, again using the binomial expansion, I can write this as 1 minus 2 phi whole square times dx square. Okay. And now what I can do is I can say the effective speed, okay, that a light particle has is dx by dt. What is dx by dt? Well, it's just going to be c divided by 1 minus 2 phi. Okay. So what this means is if I interpret this 1 minus 2 phi now as a refractive index n, okay, it's as if the light particle, as it moves through a gravitational field, has a refractive index and it's slowing down, okay, in this as it moves through a gravitational field. So that's why you're experiencing this kind of time delay, okay, and it's also a bending of the light, okay, because it's a non-uniform gravitational field. So remember that the bending is due to the gradient of phi, okay. So if the refractive index is non-uniform, that's when you have a bending, okay. That's when you have a bending of the trajectory. So, for example, at the interface between light and glass, right, or between air and glass, light bends, right? But phi is continuously bending, okay, for the kind of potential that we looked at. So you have a continuous bending of the light beam. So if you take, so remember that this phi is, it was minus 2 gm by r. So this refractive index is positive. It's greater. This minus 2 phi is positive. So this is greater than 1. Okay. So it's really like it's going from air to glass, okay, or vacuum to glass. So the transition is something like this. When you're far away, phi is 0, so n is equal to 1. When you're near us, n is equal to 1. In between, n is large, okay? So in between, it's like you're going through, let's say, mediums of more and more increasing refractive index, and then you're going through mediums of decreasing refractive index. So it's really like going through a convex lens, okay? It's going through a convex lens, okay? Light is passing through a medium of refractive index n, and it's some kind of convex lens which is focusing light. Okay. Okay. So I'll just briefly mention some current research that I'm doing. Okay. So we're using astrometric microlensing. So now we're trying to. So this effect of lensing is obviously more significant if you have a very massive object like a galaxy. If you have an entire galaxy, it can cause a significant amount of lensing. But if you have, and of course, the amount of lensing depends on this parameter, right, which was 2rs over r sun. If you have a bigger mass, then rs is larger, okay? What we're trying to do is trying to look for what is called astrometric microlensing, okay? So the idea is within our own galaxy, okay, so within our own galaxy, there should be a lot of dark matter. Okay. Now, one theory of what this dark matter is that this dark matter is made up of black holes. Okay. These black holes cannot be formed by the collapse of stars because we know the rate at which stars form, and therefore we know the rate at which they die. Okay. And if we know the rate at which they die, there are not enough stars to have produced the dark matter in the universe. There are also other reasons why these dead stars cannot be dark matter. So these black holes, if they were produced, must have been produced not by the collapse of stars, but they must have been produced in the very, very early universe, okay, during the Big Bang. So these are called primordial black holes, okay. They were produced in the primordial soup of the very early universe. Now, if these dark matter, if the dark matter in our galaxy is really made up of these primordial black holes, then what can happen is when we look at distant stars, okay, if somehow a primordial black hole passes between us and the star, it will cause a bending of the trajectory of this star. Okay. Now, how can we detect such a bending of this star? Okay. So let me show you a little movie, okay, which a PhD student of mine made, which will help you understand what the effect is. Oops, I'm not sure if this meeting, yeah, it's being recorded, right? Okay. I need to share screen from my desktop.
I have a question regarding isn't the Shapiro effect already a geometric effect? Because the geometric pattern should be calculated with the correct metric, which is basically
No, well, there are two different effects. One is due to the extra path length traveled, and one is due to gravitational time
So when
dilation.
you're talking about the extra path length, what metric are you using to calculate that path?
Extra path. So I'm always using eta mu nu, the flat metric, and with reference to that, I'm talking about extra path length versus how much is due to time dilation. Okay, so here's a picture, okay, of, oops. Yeah, okay. So here's a picture. Oops, sorry. Yeah, so here's a picture of us. Okay, this is a background object, and this is a gravitational field due to some massive object. In this case, the massive object is a primordial black hole. You can't actually see this object. Okay, and here's a star which is moving on the sky. Okay, so if you measure it for long enough, its position appears to change. Okay, now here's a, so this is what you see on the sky. Okay, so this is, let me just pause this movie here. This is the black hole. Okay, this is a
Excuse me, sir.
star, and this, sorry, yes,
So the online it is not visible.
it's not visible online.
Yeah.
1 second. Is it visible now?
Yes.
Okay, so here is a star, okay, which is behind this lens, okay, and this yellow circle, the size of the yellow circle indicates how bright it appears to be. Okay, so the size I'm using as a proxy for the brightness, and the red dots show the trajectory that the star is following. Okay, so imagine that you have different snapshots of time at which you measure this. You will actually see the star moving. Okay, now as so imagine this is a star that doesn't go behind, I mean, where you don't have gravitational lensing effects. And this is the trajectory of the star if you have gravitational lensing effects. So what you will see is something like this. Okay, the star that undergoes gravitational lensing effects will first of all experience a deflection in its trajectory. Okay, so like right when it's here, okay, it's deflected. So here's the line of sight. Here's the black hole. Here's the star. The star gets deflected here. Okay, so which is why on the sky you see it above. You see it somewhere here. Okay, if the star was here, you would measure it further deflected away from the lens. Okay, so it's always deflected away from the line joining the lens to the star. Okay, the other effect that you see is that it brightens. Okay, so it grows bright as it gets close to the as it experiences a more significant lensing effect. So this brightening is because of the focusing of the light rays. Okay, so you have to take into account the fact that many light rays are getting focused, okay, by the bending of light. Okay, and you're seeing this brightening of the star. So there are two different effects that you can use to detect the presence of this black hole now. So a star moving across the sky, normally stars will just have this kind of linear motion. Okay, at least for the time periods that we're observing them. The fact that they're moving, so these stars are moving around the center of the galaxy in circles, but those circles are over a very, very long time scale. For a good enough approximation, over 10 years or 20 years that we're observing these stars, they're practically moving on straight lines in the sky. Okay, again, ignoring the effect of parallax and things like that. Okay, what we will see is deviation from the straight line motion. Okay, this deviation is called astrometric microlensing. If you can detect this effect, it's called astrometric microlensing. If you can detect this, you can detect the presence of primordial black holes filling our galaxy. Okay, and that would be direct evidence for dark matter in the form of primordial black holes. Another way to search for these primordial black holes is using this photometric effect, looking for the brightening of a star. So even if you don't detect the deflection in its position, you can detect the change in its brightness. Okay, some stars are intrinsically variable, that is, some stars change their brightness on their own. But if you take stars which are not expected to change brightness and you see this change in brightness, okay, that could be a signature for primordial black holes as well. So this photometric technique, that is detecting the change in brightness, has been used for a while to constrain primordial black holes. So we've tried to look for it, no luck so far, but it allows us to rule out some fraction of the dark matter as being made of primordial black holes of, let's say, 1 solar mass. Okay. So the technique that I'm working on, which of course many other people are working on as well, is to use an upcoming space telescope called, a running space telescope called Gaia, which will measure positions of stars to within 1 milli arc second, okay, of resolution. 1 arc second is 1/60th of a degree. 1/60th of 1/60th of a degree. Okay, so this is very, very precise positioning of a star. So if you can, for the first time, we have such precise positions of not just one star, but millions, billions of stars in the Milky Way. So with this, okay, what we're trying to do is see what is the sensitivity that Gaia will have to detecting or ruling out primordial black holes, which are in the form of dark matter. Okay, so with that, I'll stop here. And any questions? Sorry, can you pull your mask down and just be loud?
In an ideal case, if the lens is exactly aligned with the source of the light, the flares that we see would exactly be at the same time.
Yeah, that's right. They would be, well, again, the foreground galaxy you're also assuming is point-like. That's not true either. The foreground galaxy has a distributed mass. Okay, so for point-like source, point-like lens, what you said is true. Foreground galaxy is the lens. Yeah, foreground galaxy plus its dark matter together forms the lens. Most of the mass is actually in the form of dark matter. In fact, in most galaxies, I mean, roughly what we expect is 80%, 85% of the mass is dark matter. Only 15% of the mass is regular matter, or what we call baryonic matter. Okay, and yeah, so in fact, it's embarrassing, right, that we don't know what most of the universe is really made up of. Yeah. How the flares are produced? Yeah, so you have these, so the quasar is supposed to be some kind of, okay, so for the purposes of measuring the distance, it doesn't matter how the flares are produced, as long as they flare up, right? But the theory behind it is that you have a black hole, there's a supermassive black hole, it has an accretion disk, matter falling into the black hole. This matter that's falling into the black hole has friction, so it radiates a lot of energy, okay? And it releases a lot of energy because it's falling deep into gravitational potential. So it has a lot of energy to release. Okay, it's that basically that gravitational potential energy gets released. Okay, in the form of this this energy. Sorry, I guess I'm not showing my iPad screen. Give me a second. Yeah, so here's a supermassive black hole at the center. Okay, this whole picture is of a quasar. Oops. I think it's shared on screen, but it's not visible here. Just give me a second. Yeah. Okay, so here's a supermassive black hole. This supermassive black hole is surrounded by an accretion disk, okay, of matter, accretion disk, and this accretion disk basically, as matter falls in, it undergoes friction and releases a tremendous amount of energy, which is gravitational potential energy. Now, these particles that it emits, okay, are by some complicated mechanism, they're held together by a magnetic field, okay, and they're focused in a particular direction. And that leads to a really bright, energetic flare, steady flow from a quasar. Now, what happens is as some excess lump of matter somehow falls in, okay, sometimes that can lead to excess radiation, okay, and that's the flaring effect. Okay, any other questions?
Hello, sir. Just a general question.
Yeah.
While the picture that you show about the deflection of the star from a straight path and momentary brightening of it would be the proof for a primordial black hole. But why would it be primordial black hole? It would be just to prove that there is some dark matter over there. Why particularly primordial black hole?
Sorry, can you repeat that question? I didn't understand. So you're saying this flaring could be due to primordial black hole?
Yeah, it could be just a lump of dark matter over there, right? Means uh, why the primordial black hole in particular?
Oh, because it's too small to be okay. So in the case of the astrometric microlensing that I was talking about, you can measure the mass of the lens. Okay, you can measure the mass of the lens, and the mass of that lens, you can measure the mass, and roughly you can measure its compactness. Okay, so roughly you have a measure because you're measuring roughly its gravitational field. If you measure this and you know it's sufficiently compact and it's a one solar mass object, then it has to be a black hole.
Okay, okay.
And not something else. Okay, thanks. I think we'll stop here. Okay. Thank you. Bye.